in this segment, I'm going to tell you about the Burali-Forti paradox. It's a result in set theory that shows that there is no such thing as the set of all ordinals. So I'm going to show you why this has to be true first, and then we'll talk about why it's important. There is a formal proof of this result, but I'm not going to give you that formal proof here because so far we have not been working with a formal definition of ordinal, and a formal proof would require the formal definition. So what I'm going to do is I'm going to give you an informal proof, which is based on our informal conception of ordinal. So our informal proof is going to proceed by reductio. We're going to assume the opposite of what we want to prove, and then use it to derive a contradiction. So we're going to assume that there is a set of all ordinals. So let's assume that there is a set big omega which consists of all ordinals. And we're going to derive a contradiction by asking the question, is omega an ordinal? And as we'll see, there's an argument for thinking that the answer has to be yes, and an argument for thinking that the answer has to be no. And of course, the answer can't be both yes and no, so we must have gone wrong somewhere, and where we've gone wrong is in making our assumption. So let me give you the argument for yes first. So remember how we're thinking about ordinals. They're introduced in stages, where at each stage you introduce as a new ordinal the set of every ordinal you've introduced in past stages. A consequence of that way of thinking of ordinals is that we have this result, that an ordinal is just a gapless set of ordinals. Where what it is for a set of ordinals to be gapless is for it to contain no gaps. In other words, for it to be the case that whenever our set contains an ordinal, it also contains every ordinal smaller than that. So this is a principle that follows from our understanding of ordinals. And notice that if our set omega existed, it would be a gapless set of ordinals. It's certainly a set of ordinals, and it can have no gaps because it contains all ordinals. So that's our yes answer. We get our yes answer because omega is a gapless set of ordinals. And now let's look at our no answer. The way to get our no answer is to say, well, suppose otherwise. Suppose that omega was an ordinal. Because it's the set of all ordinals, that means that omega would have to be a member of itself. But omega can't be a member of itself because, again, remember how we're thinking of ordinals. You introduce a new ordinal by putting together in a set every old ordinal. So it's impossible for an ordinal to be a member of itself. So we reached an argument that omega can't be a member of omega, and therefore that the answer has to be no. So something has gone wrong, so our assumption is wrong, so there is no such thing as a set of all ordinals. There are two reasons why this is an important result. The first is that it tends to be interpreted as meaning that there are too many ordinals to form a set. Now, that's not obvious on the basis of what we've done now, but it is a consequence of the standard way of thinking about set theory. So if that's right, if this result means that there are too many ordinals to form a set, then that gives us a sense of how many ordinals there are. They're not just infinitely many. It's an infinity so big that it cannot be contained in a set. So that's remarkable on its own. But there's another reason why this is an important result. And it's that it destroys what might be described as the naive conception of set. So let me tell you what that is. So the naive conception of set is the view that if you take any predicate f you want, the set of f's exists. So that set exists for any f. So for example, if you let f be elephant, this principle entails that there is a set of elephants. And it also entails that if you let f be ordinal, there is such a thing as a set of ordinals. So by the Burali-Forti result, the naive conception of set cannot be correct. And this is a momentous observation. Because if you can't get a set by just picking some things, the f's, and saying they form a set, then how are we to know when some things can be collected into a set and when they can't be? As it turns out, we do not have a fully satisfactory answer to this question. So what set theorists do nowadays is that they recognize that you can't use the naive conception of set. So nobody endorses a principle like this that says that for any f's, you have a set of f's. And what they do instead is they cobble together a collection of axioms. And the standard axioms, the ones everyone uses, which are called ZFC, have the feature that as far as anyone knows, they're consistent. So unlike the naive conception of set, but also that they're strong enough to be able to do real mathematics. So in a sense, they're very nice axioms. They allow us to do what we want to do without lapsing into contradiction. On the other hand, they are not super principles. They do not derive from a unified conception of set. So a consequence of the Burali-Forti paradox is that it is not clear that we can base our set theoretic thinking on a very coherent conception of set. There is another way of getting to that same result, and in fact, it's the more famous way, and that is not via the Burali-Forti paradox, but via what is sometimes called Russell's paradox. So Russell's paradox also undermines the naive conception of set, but in a more straightforward way. The way it works is you just say, well, suppose that it really were true that for any f, you could form the set of f's. Then in particular, you should be able to form this set, which you're going to call R. The set of things which are not members of themselves. And then you can ask the question, well, is it the case that R is a member of R? Well, let's see what it would take. So by definition, R is a member of R if it satisfies this condition, if it satisfies the condition of not being a member of itself. And that's a contradiction, because it says that R is a member of R if and only if it isn't. So from the assumption that this set exists, we could prove an absurdity. So it cannot be that this set exists. So it cannot be that the naive conception of set is correct.